All right, welcome back to our Design for Additive Manufacturing class. Today we're going to talk a little bit about design guidance for additive, particularly for SLS. And if you recall back from one of our earlier lectures, we talked a little bit about restrictive versus opportunistic design for additive manufacturing, and how even in opportunistic design for additive manufacturing, where we're trying to really take advantage of additive to the most extent possible, we still need a little bit of guidance about what we can and can't build in additive, right? And if we're trying to, on the other end of the spectrum, just fabricate an existing part with additive, we need lots of design for additive manufacturing guidance, because we need to know what we can and can't make, what types of minimum feature sizes, what types of tolerances, and that's where we're at right now. All right, so what I'm going to talk about today really feeds off of an American Makes project that we conducted a few years ago with a couple of my graduate students, Jared Allison and Connor Sharp, as well as some folks at Stratasys Direct Manufacturing, which is the same place we visited a few weeks ago here in Austin. And so they built lots and lots of parts for us, and we did metrology on those parts to try to develop some of the guidelines that you're about to read. All right, in terms of motivation, we all know that polymer powder bed fusion in SLS has a lot of advantages in terms of being able to consolidate parts, build complex parts, functional end-use parts like ductwork, as you see here. The problem is that it's sometimes difficult to get your parts right the first time because we don't have a lot of guidance in terms of what we can and can't make. And so that is really important for encouraging widespread adoption of this process. Many corporations have done some proprietary studies to try to characterize the process to see what they can and can't build, but they often keep those as industry secrets, as trade secrets that they don't want to share with other companies. There have also been some studies, public studies by academia and by some SLS manufacturers like EOS, but they've all been very limited in scope. And so the whole point of this study was a more robust public database that we could use to build to basically statistically characterize the SLS process so that we can get lots of information on what we can and can't build and what types of accuracy and resolution we can get. All right, so first I want to highlight that the information I'm presenting today is available on a web tool. And all you have to do is go to designforam.me.utexas.edu. And a lot of the information that I'm presenting today, as well as some additional information, will be available there. And I'll give you a little tour of that as well towards the end of the video. All right, so in order to capture all the data that I'm going to present on the SLS process, we started with designing a test cube. All right, here's an image of that test cube. You can see here on the left is in a design of the test cube as it was built. Each one of the dimensions here is 2 inches by 2 inches by 2 inches. All right. We built it small and compact like that for a reason, because what we wanted to be able to do was to take this test cube and insert it into lots of builds at Stratasys Direct, lots of existing builds, so that we could repeat the build of this test cube over and over and over again and start to compile some statistics about the process that we could use. So you build this test cube, it's all one piece, but then after you've built it, then what you can do is you can snap off individual sections of the test cube. And you can see there's 1, 2, 3, 4, 5 separate plates, plus there's a build plate, a platform that everything's attached to, that these 5 plates snap off of, and then also some additional features here which are going to be used for surface finish. Okay. So if we look at this test cube, you can see within this 2 by 2 by 2 inch cube, all the different features that we incorporated, right? So first, if we look at the bottom here, you'll be able to see that there were some test features here that looked at gaps, right? And they looked at gaps as a function of the thickness of the walls in which they're embedded. So you'll see that these walls here get thinner and thinner and thinner. So we can see whether our resolution or accuracy of these gaps changes depending on the thickness of the walls. We did the same thing with holes, and here you can see the changing wall thickness in which these holes are embedded. And these holes here you can see range in diameter from fairly large on one end to quite small on the other end. So we could see what size hole is the minimum size hole that we can resolve, and how does that depend on how thick the wall is. We incorporated some thin walls as well, and you can see those here. I'll give you more information on that. We looked at some lettering, right? So some of it was raised lettering, and then up here you'll see some was embedded lettering that was indented into the material. We looked at different size fonts from really small to really large, and then we also adjusted how much they were raised off of the surface or how much they were embedded in the case of the embedded letters. We also looked at some linear accuracy features there where we could look at the distance between different features and how accurate that was compared to our CAD model. We've also had some hinged parts here. Many of you are interested in clearance. We also did some thin rods, some of which went from side to side and were supported on both ends, others of which were protruding and supported on only one side. We also incorporated some features for cylindricity, although I'm not going to report on those results today, and then also some different angled surfaces for surface roughness. Okay, so all these features we were able to measure from this single test cube. Okay, with this test cube, we conducted an experiment and we varied several things. So the first thing we varied was the material, right? So we could have either PA12, which is nylon 12, GFPA12, which is glass-filled nylon, or FRPA11, which is a fire retardant nylon 11 used primarily in the aerospace industry. And you can see these materials here on the side of the chart. We also varied the orientation in which that cube was built, and you can see that listed here in the chart with 3 different orientations. We also, and I'll show you in a second what those orientations were. We also varied the location of the test cube within the build envelope. So I here is for interior, E is for exterior, whether it was in the center of the build chamber or whether it was near the outside of the build chamber. We also built the test cube on 5 times on the same machine, and we also built 3 copies on different machines so we could look at machine to machine variation. Altogether, if you look at every single one of these squares over here in the test matrix, we built 144 total cubes. So let's look at a couple of the different things, experimental variables. One was location, right, versus interior versus exterior. So exterior means in the outer 2 inches of the build chamber. Interior means away from the outer 2 inches of the build chamber. Just to see if sometimes the exterior of the build chamber is a little colder than the interior, to see if there were some effects. Orientations are important, so take a look here at the axes down here in the bottom, right? We've got X, we've got Y, and we've got Z, right? And we can orient this this test cube in different orientations relative to the build plane, right? So XY plane means that this bottom structure that holds everything together, that base plane, is built in the XY plane. Okay, YZ means that basic structure that holds everything together is built or XZ, sorry, is in the XZ plane. Here's that basic structure. YZ means that base plane, which you'll see back here, is built all in the YZ plane, and that can have a really important impact on properties, right? So let's look at some of the results that we got out of the tests, right? So remember that we did 144 total cubes, 3 different materials, 1, 2, 3. Within those materials, we have different orientations, and then within those orientations, different locations. And then we try to build them repeatedly on a single machine and then build it on a separate machine as well. All right, so let's look at some examples of these design guidelines, right? So for every single one of these features, whether it's holes or gaps or thin rods, what we tried to do was to first give you some general guidelines of things to think about. Resolution, what you can and cannot build. If they become too small to resolve, we'll let you know about that. Accuracy, so just because you can build something doesn't mean it's going to have exactly the same dimensions that you specified in your CAD file. An explanation of why these things are happening, right? So it's not just completely out of the blue. We also did an ANOVA analysis to see if material, orientation, location had effects on the accuracy and resolution that we were observing. And I'll talk about that a little bit for the first example, but then I'll leave the rest of that for the online tool. So let's look at the first geometric parameter that we want to look at. This is hole diameter as a function of wall thickness, right? So you'll notice here that we've got hole diameters that range from 0.8 millimeters up to 2.6 millimeters. And then we have wall thicknesses here that range from, at the thickest, 10 millimeters down to the thinnest 1 millimeter down here. All right, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 holes in every thickness. And then we've got 1, 2, 3, 4, 5, 6, 7 different wall thicknesses. So a total of 63 holes in each one of these build plates. One of the things we found is that the holes are generally undersized compared to nominal holes. So if this is the hole that you want to build, the hole that you actually build will be a little bit smaller. There's a number of reasons for that. One of the primary reasons is something we call over-centering, right? So if the machine is centering all the material around this hole and behind it, right? That region's going to get hot, right? And if it gets warm enough to center the material right here at the boundary of the hole, it's probably going to get warm enough to start centering some of the material inside the hole as well, right? And so you get this over-centering effect that diminishes or undersizes the hole from what you had specified. They're most undersized when they're oriented with the central axis parallel to the z-axis, okay? So that means that if the z-axis, right, is running into the page here, they will be the most undersized, right? So a hole built that way, so looking top down, right, if the hole is built that way, right? Those will be the most undersized. You'll see the most sort of over-centering. And if, on the other hand, that hole is built parallel to, say, the x-axis or to the y-axis, so it's going across the build platform, it won't be quite as undersized. And we'll talk a little bit about that later on. Also, the hole accuracy and resolution is dependent on the wall thickness. So the thicker the wall, the harder it is to resolve these holes. So once you get to these thick walls, you'll find that you can really only resolve some of the thickest hole, the largest holes. And if you want to resolve some of the smaller holes, you'll need something much, much thinner. Okay. So here's a plot of resolution. So let me tell you what you're looking at here. So across the top here, you can see you've got hole diameter from 2 millimeters all the way down to 0.8 millimeters. And then across from top to bottom, you've got different wall thicknesses from 1 millimeter at the top to 10 millimeters at the bottom. All right, so everything here that's red means that it usually doesn't build. So 25% or less of the parts that of the holes that we built actually resolved. So the hole was there after the build. In yellow, it means it's somewhere between 25 and 75%. And then green means that it's somewhere greater than 75% of the holes resolved. Okay. One of the things you'll notice here is if you want to resolve really small holes, let's say a millimeter or 1.2 millimeters, you really need to have a really thin wall in order to resolve those. If you're content with a much thicker hole, say a 2 millimeter hole, right, 2 millimeter diameter, then your wall can be much thicker. So almost all the holes, the 2 millimeter holes, resolve all the way down to as much as 4 millimeters thickness in cell walls. And then quite a few of them resolve even if you have a 10 millimeter thick cell wall. Here's a look at accuracy. And this is the nominal size for this particular hole, which looks like it's about 2.6 millimeters. That's as designed, right? That's nominal or as designed. And then here you have the as built, what actually built. And here on this axis, we've got wall thickness. And this is, of course, what's measured. And these are standard errors, right, over all the samples that we measured. And what you'll find is as the wall thickness gets thicker, right, the over-centering gets greater, right, and the actual diameter of the hole gets smaller and smaller. And that's most likely because as the wall gets thicker, you get more and more over-centering, right? You get more heat built up in the wall, and that causes those holes to over-center a little bit more. Okay. On the web tool, you'll find that for each feature an ANOVA analysis looking at the significant effects. And let's take a look at that, what that looks like, what those tables look like, and what they mean. All right, so let's look down here at this table and you'll see here, first of all, percent significant. All right, so these are holes. And so there are, I think we said there were 63 different holes, right? Holes of different sizes, each one built in walls of different thickness. This tells you that, and then the different letters in here are material, orientation, location, and then this is an interaction effect between two different variables. So what this tells you is that material had a significant effect on hole diameter for 100% of the features we looked at. Orientation had a significant effect for 60% of the features, and so on. So in that case, material had a really strong effect on what we observed in terms of hole diameter. So there was more overcentering for some materials than for others. The average mean distance difference down here, 0.2 millimeters in this case, means that if you switch from one material to another, on average, you can see is about a 0.2 millimeter change in the hole diameter based on what we observed from the holes that we built, right? So what's the explanation for some of the things that we've seen? So overcentering and shrinkage cause hole diameters to be smaller than the nominal value. Overcentering is typically worse when the surrounding walls are thicker because of the buildup of heat. So holes through thick walls tend to be more undersized than the same diameter hole through a thinner wall, right? So if you have these walls and some of them are really, really thick and others are really, really thin, and you try to cut the same diameter hole through it, this one will undersize even more, right? And so what you'll actually get is much smaller. This one will undersize a little bit less, right? And what you'll actually get will still be smaller, but not as much of an undersizing as you would in the thicker walls, okay? The other thing we found is that if you orient those walls, let's say X, Y, Z, right? So walls that are oriented in this direction, right, through the part, tend to be a little bit less undersized than those that are oriented in this direction through the part. And that could have something to do with the buildup of heat. It may also have a little bit to do with the fact that layers here are determining, because the layers are going through like this, the layers are helping determine the hole diameter here, and layers are really thin, 100 microns. Versus in this case, for the Z direction hole here, the spot size and the scanning of the laser is determining the hole size. And in this case, the spot diameter of the laser is more like 0.45 millimeters versus a 0.1 millimeters for the layer thickness. We may also be getting a little overcentering just due to the heat in the plane here for the Z direction holes. All right, so the next feature, surface finish as a function of orientation. So here you can see we have a number of tabs that we could break off, and we measured the surface finish on each one of those tabs, oriented from 0 degrees, 15 degrees, 30, 45, 60, and 75. What we found was that the surface roughness was best on the flat surface, and then worse on the inclined planes. And that the surface roughness varied between 20 and 35 microns, which isn't surprising because that's on the order of the powder sizes that we're using, which are about 50 microns. Here you can see that surface roughness here. So here's the inclination angle on this axis. And then here you can see the surface roughness measurements here. And you can see that the best surface roughness was on the 0 degree surface. It got worse as it started to incline even a little bit to 15 degrees, and then it gradually got a little bit better till you got back down to 90 degrees. All right, the explanation is that surface finish is typically best on flat surfaces because they avoid the stair stepping effect, right? And as you start to incline, you'll see stair stepping that you see here, and then it gets a little bit better as you get towards vertical. And vertical surfaces are much better than tilted surfaces, but often not as good as flat surfaces, maybe because of slight misalignments from layer to layer. Next, let's look at linear accuracy, right? So this is the part down here that we use to measure linear accuracy. You can see a cross section of it, a view of it over here, and you can see that there are different features spaced different distances apart, right? And so we were measuring the distance in between these features, inside these features, so that we could measure linear accuracy or the placement of features relative to one another. One of the things we found is that linear accuracy is better when the features are distributed along the z-axis. So if this is the z-axis, that it's better than if those features had been distributed along the x-axis or the y-axis. We'll talk about that in a little bit. And the actual distance between features is generally a little bit less than the nominal or as designed value specified in your CAD file. We also found that it doesn't really scale with size, which indicates that this is a resolution or over-centering problem and not a shrinkage problem. Because if it were a shrinkage problem, the larger the part or the larger the gap, for example, the more you would expect it to undersize as it's built. But that's not happening. So let's look at accuracy here. Here you can see again, the red line here is the nominal as designed. Right, so what you would include in your CAD dimension in the blue here is as built. You can see that these distances between features tends to be quite good, and the difference between the nominal and the as designed is somewhere around 0.2 millimeters on average. Okay, the trend appears to be independent of size, so that these two lines are parallel. So what's the explanation for this? Since the accuracy doesn't appear to depend on size, right? The undersizing must not be due to shrinkage. It's most likely due to modest amounts of overcentering and also to the resolution limits with respect to layer thickness and spot size, right? So if you have something that you're building in the plane, right? Say X, let's say this is the X direction, and so which means that you're looking at this from the front of the machine versus if you were trying to build something like this, right? And this is the Z direction. One of the things that's going to help determine your accuracy here are the layer thicknesses, right, that come across, right? And each layer thickness is 100 microns. In this case, as you go across in the X direction, one of the things that's going to help determine your layer thickness is the spot size, right? When in this case, it's 450 microns or 0.45 millimeters. So the resolution in the Z direction is in an additive, in an SLS process is often better than the resolution in the X or Y direction, which may account for why the linear accuracy is a little bit better for features that are distributed in the Z direction than for features that are distributed in the X direction. All right, so our next feature, let's look at gaps. So gaps, you can see our test feature for studying gaps. They're very similar to holes. They're just rectangular insertions in the part. And you can see here we varied them from 1.4 millimeters in width to 2 millimeters in width. And we built them on a part that ranged from 10 millimeters thick all the way down to 1 millimeter thick. And here's a look at the accuracy, right? This is again the as designed from the CAD file. And then this is the measured. And once again, these error bars here are standard error across all the different gaps that we measured. And you can see that this undersizing appears to be pretty consistent at 0.2 millimeters once again. There doesn't appear to be a very significant dependence on wall thickness, which is a little bit different from what we saw with holes. So what's the explanation, right? Overcentering and resolution are most likely the greatest contributing factors to those undersized gaps. One of the important things to remember is they're undersized, just like holes and other subtractive features. The undersizing of gaps was more pronounced for nylon 11 than for nylon 12 or glass-filled 12, and it could be because nylon 11 has a higher melting point and a smaller window of processing temperatures than the other two. So that could be accounting for that. Slightly different process settings. All right, here's the next feature that we look at is thin walls. And here's our test part for measuring thin walls. You can see walls here at the top that are 0.2 millimeters. That's only 2 layer thicknesses thick. Very, very thin, all the way up to 0.8 millimeters here. One of the things we found is that walls that are 0.5 millimeters thick resolve well regardless, but if they're smaller than that, you may only be able to resolve them if they're oriented in one direction, specifically if these thin walls are parallel to the build plate. So let's look at, in this case, this is our nominal. This is our nominal CAD measurement, right? And then this is our measured values. Again, the error bars here are standard errors across everything that we measured. And you'll see that these thin walls, in this case, instead of undersized, they're oversized, just a little thicker than they should be by, again, around 0.2 millimeters. Doesn't seem to depend too much on the thickness of the wall, but thicker walls are sometimes oversized a little more than thinner ones. Okay. In terms of resolution, so resolution is a little different from accuracy. Resolution determines what we can see, what actually ends up in our final structure versus what disappears. Accuracy, on the other hand, tells us how accurately we can build something, assuming we can actually build it. So here you'll see if we have thin walls that are parallel to the build platform. So if we have thin walls and we're trying to build them this way, right? Knowing that up here, you'll see the axes here. We've got X, we've got Y, we've got Z. So in this case, at least 75% of the walls were buildable for all of the different dimensions that we looked at. Even for those really thin 0.2 millimeter walls, we're still able to build 77% of the ones we tried to build. If we take those thin walls and we orient them in the XZ, on the other hand, right? So if they're built this way, or if we build them in the YZ, right? Or if we build them in the YZ, then we have a lot more difficulty resolving these thin walls. They're no longer parallel to the build plane. Their resolution is determined by spot, right? Remember, the spot size is more like 0.5 millimeter. And here they're determined by the layer thickness, which is around 0.1 millimeter. Right? And so in these cases, we can only reliably resolve walls that are at least 0.5 millimeter thick, right? Everything else is very, very difficult. On this side, it's very, very difficult to build it, okay? So explanation for what we're seeing here, right? Overcentering plays a large role in the accuracy of thin walls. In this case, however, the overcentering causes the walls to be larger than their nominal dimension. And we want to think about walls as being an additive feature, where the laser scans the feature geometry. Gaps and holes, on the other hand, are subtractive features, where the feature geometry is determined by voids. So overcentering leads to subtractive features like a hole, right, being undersized. And then it leads to additive features, right, like a wall, right, being ever so slightly oversized, right, a little bit oversized. The resolution of thin walls is strongly dependent on orientation, like we talked about in the previous slide. So walls built in the XY plane can be resolved at thinner thicknesses. If you want to orient them in the XZ or YZ planes, then they need to be a little bit thicker. So we can get all the way down to 0.2, 0.3 millimeters if they're parallel to the build platform, but they need to be at least 0.5 millimeters if they're orthogonal to the build platform. Rods, all right. So in this case, you can see that we built rods of varying diameters, right? Some of them are attached to both sides of the both sides of the object. Others are cantilevered, and here you can see a short cantilever. And then some are cantilevered and long, right? One of the things we found is that rods that are at least 0.6 millimeters in diameter tend to resolve well. If they're thinner than 0.6 millimeters, they generally don't resolve. And that doesn't seem to matter whether they're attached on both ends or whether they're cantilevered. So here's a look at the resolution, right? So again, if you look here at 0.6 millimeters here, anything greater than 0.6 millimeters seems to work well, whether they're supported rods, unsupported rods that are long, or unsupported cantilevered rods that are short. The reason to support rods, though, could be that it might help avoid damage, right, during breakout and post-processing. So that still may be a good thing to do. The explanation here is that the resolution results for thin rods suggest that neither aspect ratio nor being supported to both ends has a substantial effect on the resolution. The self-supporting SLS powder bed does a good job of securing the rods in place during the build process. So you can generally resolve anything reliably in terms of rods as long as the diameter is greater than 0.5 millimeter. All right, hinges. So many of you are thinking about building hinges and movable parts. So in this test build, we tried two different clearances, shaft clearances. Here you can see this part here is the shaft, and this is the knuckle that's revolving around it. We tried a 1 millimeter and a 0.6 millimeter clearance to see if either of them would resolve. It would be nice if we had tried more, but we didn't have enough space on the test cube to try more things. One of the things we found is that with a 1 millimeter clearance, most of our parts resolved such that you could move the shaft relative to the knuckle. But with a 0.6 millimeter clearance, most of them did not resolve such that the shaft and the knuckle fused to one another. So what's the explanation here? Hinges with a shaft clearance of 1 millimeter generally resolve successfully. 0.6 millimeters generally do not. Right? So as we were talking about in linear accuracy and gap accuracy, over-centering and accuracy resolution problems tend to affect measurement results by about 0.2 millimeters. So if we use this rule, all hinges with a shaft clearance greater than 0.6 should be able to move freely. So we've got, this solid shaft here, and then we've got this knuckle that's around it, right? And that's also solid. And here we're looking at this clearance, right? This C is the clearance, right? So if this, for example, if the shaft overcenters by 0.2 millimeters, right? And if the hole overcenters by 0.2 millimeters, one would think that we'd still have some space in there for movement. But it turns out that that doesn't seem to be happening in these tight fitting moving parts. So we think what may be happening is that you've still got some powder trapped in here, right? So if this over centers out to here and this over centers into here, you've got trapped powder in the middle. It's heating up and it may be centering, right? The over centering may be magnified by having that powder trapped inside. And so that's causing this fusion between the shaft and the knuckle and the lack of motion. So you really need to be having clearances closer to 1 millimeter in order to make sure that they resolve. And so when you really think about it, but it has to be 1 millimeter on both sides, right? Clearance here of 1 millimeter and also a clearance here of 1 millimeter as well. So it'll cause a little bit of noise, a little bit of looseness in the motion of it, but at least it won't fuse together. All right, let's look at the next feature. We're almost done. We've got this feature plus one more to review. And so this one is lettering. And so we tried lettering that was embedded. So you can see that over here. We also tried lettering that was raised. For each one of those, we tried different font sizes, right? From small to large. We also tried raising the height of the letters, right? And the depth with which we embedded them. Okay. And what we wanted to see was whether it would resolve. So here's a pass you can see down here, an intermediate, and a fail, right? A fail means you really can't tell anything about what's being printed. An intermediate is you can kind of make it out, and a pass is that the lettering is very clear after it's been bead blasted. So here's a look at the resolution. So if the lettering is embedded, okay, you can resolve all of the fonts that we tried, right, at any of the depths that we looked at. If the lettering needs to be raised, then you really need to try some larger fonts, regardless of the depth or the height with which that lettering is raised. So the moral of the story is try to embed your lettering because you'll get better resolution. Part of that explanation is that raised lettering has a lot of really fine positive features. So let's go back and look at this. So look at these really fine, very thin walls that have to be raised here. Okay, and it's really difficult to do that in SLS, which is why you have to have a 16-point font to be able to raise the lettering. Another The embedded lettering then is less susceptible to these defects because it's a negative effect that's scanned by the laser. So as long as the laser can outline that letter and then fill in around it, then you'll be able to resolve it, right? So these raised letters in many ways are similar to really thin, unsupported walls. Another good general guideline is to use fonts like Arial with a constant stroke width. So if you make an A, in Arial, it'll look like this. Whereas in some other fonts, like a Times New Roman font, you may see it get thinner and thicker in some places, depending on how it wants to resolve the letter, right? So some areas may be thicker than others and others thinner. And so you risk having these thinner parts of the letter disappear because they're not thick enough to resolve. So finally, let's look at snap fits. So snap fits here we tested, you can see there's a slot over here on this side, and there are pegs here that were printed on this side. We snapped off this entire feature and then tried to fit the pegs into different slots, right? And these pegs were all 3 millimeters, and the slots here ranged from 2.9 millimeters, which was a little bit smaller than the peg, all the way up to 3.5 millimeters, which was a little bit larger. So the offsets between the peg and the slot, so an offset between 0.15 and 0.2 millimeters seemed to work best. And that was to account for the under oversizing that we were seeing throughout the process. So here's a look at the under oversizing. So anything less than 0.15 has a lot of trouble resolving. Anything from 0.15 to 0.2 has a little bit better chance of resolving. And so here, down here in this picture, you can see what the offset, how it's determined. So here we've got the peg here is 3 millimeters across. The slot is 3.3, and that leaves a 0.15 millimeter clearance on either side. And what we were looking here was a snug fit, not too loose and not too tight that you couldn't fit them together. And so we found that a 0.15 to a 0.2 millimeter offset was the sweet spot. And the explanation here is that the ideal snap fit offset is slightly less than 0 millimeters. So typically, if you're going to make one using conventional fabrication, you'll build both the peg and the slot either at the same dimension, or maybe build the slot just slightly smaller so you get a nice snug fit. But for SLS, it requires a positive offset of around 0.15 to 0.2 millimeters. Over-centering causes the peg to be oversized and the slot to be undersized, and so that's what's accounting for that additional offset that's required. Okay, so finally, the last thing I want to point out here is that we have a web tool that provides all of this information, plus an interactive chart tool that will allow you to explore all sorts of different effects. So if we go to this page, designforam.me.utexas.edu, you'll be able to find a website with all the results that we discussed just now. Plus, you'll find this interactive chart tool that will allow you to explore the effects of material choice, orientation, and location in more depth. So let's take a really quick look at that website. Okay, so designforam.me.utexas.edu. And we're going to go in here to polymer powder bed fusion. We're going to go into, you can see design guidelines here. If we click on that one, for example, we'll be able to see some of the design guidelines that we had covered earlier in the talk. And if we click on interactive chart tool, for example, what we'll be able to do there is go to an interactive chart tool that will allow us to look at a number of different combinations of materials, location, etc. So let's go into this interactive chart tool a little bit. All right, and I'm going to use the chart tool here. All right, and so here we see a number of graphs. And so let's focus first of all here on what's happening here towards the top of the build, top of the window. We can see this is data for holes, which we would recognize as the same data that I reported for holes in the presentation that I just gave. But we can, if we want to, we can look at different orientations, for example, right? So let's look at XY orientation, right? So if the holes are in the XY orientation, you'll see that they're a little bit better, a little bit closer. The blue line here is what we measured for the XY orientation. The green dotted line is for all the data in any orientation. And the red line here is the nominal. And you'll be able to see that if the holes are built in the XY orientation, if the part itself is built in the XY orientation, such that the holes are moving, that the length of the hole is in the XY plane, you get slightly better than average resolution. If on the other hand, you build the part in the YZ orientation, so now these holes are running up and down the build chamber, so that if you traveled through the hole, through the length of the hole, you would be traveling in the Z direction, then you'll see that the holes are even more undersized, right? So the deviation from a nominal dimension is even worse, and you can see a lot more red creeping up into this chart. So these orientations are with respect to the test cube itself. So you have to go back to one of the first slides in the presentation to look at the orientation of the test cube and see how the holes were oriented there to make sense of this data. You can also look at different materials, right? So this is what happens with all materials. If we look at, say, nylon 12, we can see how the results change. We could look at nylon 11, for example. Remember how we said that nylon 11 seems to be a little bit worse for accuracy, partly because its processing window is so much smaller. And we're seeing that again here. You can see in this particular chart where when we go to nylon 11, the blue line for what we've measured for nylon 11 is farther from the red nominal line than the average data. But if we look at something like glass filled, it's a little bit better. And if we look at regular nylon, right, it's even better. So that process seems to be tuned for the best accuracy. All right, so you can go here and you can play around with this a little bit as much as you like. We can also, if you want to look at just the general design guidelines for powder bed fusion here, you can see those coming up, and you can read more here about how the data was gathered, right? The scope of the study. You can see a little bit about the materials, the orientations, the location within the build chamber, how we measured different things, how we interpreted accuracy and resolution. And then you can also see general guidelines for all the features that we looked at. So surface roughness is here, linear accuracy is here, gaps are here, and for each one of these you can also see this significant effects table, right? So material, orientation, location, what had a significant effect on, say, gap accuracy for different wall thicknesses, right? And you can also look at the mean differences. So if it did have an effect, material had an effect, how much did it change the gap thickness from, say, going from PA12 to glass-filled PA12? Well, then that was about 0.16 millimeters on average. So you can see all that information here. Okay. All right, so from there, I'm just going to acknowledge, I mentioned the graduate students, particularly Jared Allison and Connor Sharp, but also some undergraduate students who helped gather this data, and the folks who sponsored the study. All right, so hopefully this information will be very useful for you as you start to dimension your parts for SLS.